This is a video for Edexcel Further Pure 1, Coordinate System Section 2.5, Focus Directrix Properties of Hyperbole. Well, we've seen already the idea of eccentricity being the focal distance PS divided by the distance from the directrix of a point P being equal to E. And if E lies between 0 and 1, that produces an ellipse. If E equals 1, a parabola. Now we're going to consider the case where E is greater than 1, and this produces a hyperbola. So if E is greater than 1, then what we have is that the distance from the focus is going to be greater than the distance from the directrix. So we can see on this diagram of a hyperbola that PS here is going to be greater than PM. What we have is the Cartesian equation we've seen before, where we've got minus y squared over b squared, whereas for the ellipse, of course, it's plus y squared over b squared. The eccentricity being greater than 1 that we've just been talking about. You'll see that the expressions for the foci and the directrices are exactly the same as for the ellipse. However, because E is greater than 1, then AE is much bigger than A divided by E. So this time we've got the directrix being closer to the origin than the focus. So the directrix is lying between the origin and the focus S. On the opposite side, we have a symmetric focus S dash and its corresponding directrix x is equal to negative A over E. Now we can put these facts together to produce an important result for the hyperbola, which is b squared is equal to a squared e squared minus 1. And again, you'll see that that's very close to the expression that we had for the ellipse. And the proof of it is indeed very similar to the proof that we went through for the ellipse. We're going to use Pythagoras' theorem in this triangle here to give us ps squared, so that will be the base length here, which is x minus AE, so x minus AE all squared, plus the height of the triangle, which is y squared. PM is going to be x minus A over E, so that's x minus A over E, and therefore PM squared is going to be equal to x minus A over E all squared. And we can equate these two expressions using the fact that PS squared is equal to E squared PM squared. And on the next slide, in fact, I do that. So these are the expressions that we've just got. Notice that PM squared, we can take out E squared as a factor on the denominator, leaving us with the expression EX minus A all squared over E squared. So that means that when we have E squared PM squared on the next line, the E squareds cancel out, leaving us with this equation. Now, I'd like you to pause the video and just check through the next lines of working. It is just simply a case of multiplying out the brackets and rearranging to get it in the form that we have, looking like the standard expression for the hyperbola. You'll see then what we've got is y squared divided by this expression a squared e squared minus 1. And of course that is b squared. So we have this important result, b squared equals a squared e squared minus 1. Right, I'd like to look at an example now which uses this result in its solution. So here we have a hyperbola, and we're asked to find the eccentricity E, and then to sketch showing the directrices and the foci, and also the asymptotes. Well, we're going to do that by getting it into its standard form, x squared over a squared minus y squared over b squared equal to 1. Once we've got that, we can get values for a squared, b squared, and use the expression that we've just proved to calculate E. So here it is, we've divided through by 36, and we can see therefore that a squared is equal to 9 and b squared is equal to 4. So b squared equal to a squared e squared minus 1 means that 4 must be equal to 9 and then e squared minus 1. So dividing by 9 and adding 1, e squared is equal to 4 divided by 9 plus 1, which is 13 over 9. And therefore e is equal to root 13 divided by 3. So that's the eccentricity, root 13 over 3. Once we've got the eccentricity, we can then calculate the value of the foci, so that we have those at AE. AE is just 3 multiplied by root 13 over 3, which is root 13. And therefore S, the focus on the right hand side there, must be at root 13, 0, and S dashed is at negative root 13, 0. The directrices are at plus or minus a over e, so that's 3 divided by root 13 over 3, so 3 multiplied by 3 over root 13 is equal to a over e, so that's 9 over root 13. So we have negative 9 over root 13 and plus 9 over root 13 for the directrices. X equals negative 9 over root 13 and x equals plus 9 over root 13. You could rationalize the denominator there if you wish. The asymptotes are y is equal to plus or minus b over ax. Well, we know that b is equal to 2 and a is equal to 3, so we have y is equal to 2 over 3x and y is equal to negative 2 over 3x. And there we are, complete. Let's look at that neatly on a diagram. There it is. Now, just a hint, when you're doing this sort of thing and you're asked to sketch, there's no need to try and get these looking exactly as to scale. So your sketch is literally just that. You simply draw in, as I did, a blank hyperbola with asymptotes and directrices drawn in, and then calculate their values. Don't try and get your graph looking accurate. Okay, that's the end of this particular video, other than to look at the summary of the results that we have. And here we have the hyperbola. But the thing that I've already pointed out to you is that the expressions for foci, directrices are exactly the same. And you'll see then that the only difference is that the value of E changes. In fact, for the parabola, we also have E being equal to 1, so x equal to negative a is also negative a over E. And the focus, the single focus, when x is equal to 1 rather, is at AE, which is a times 1. So these expressions don't change. There is a difference in the expression for b squared. The ellipse has 1 minus e squared, whereas the hyperbola we've just seen has e squared minus 1. Right, in the next video we'll be looking at the idea of tangents and normals to the ellipse.